All right, so let's get right into it. So many of you may know, and some may not, that IBM actually makes their own SSDs for our enterprise storage appliances. We call these flash core modules, or FCM, and we also consider this a computational storage device. So currently we are on our third generation of FCM, and it is enterprise QLC 2.5-inch U.2 NVMe form factor. So it's a dual port 2x2. We are only using QLC for our FCM drives, and we offer 4 capacities ranging from 4.8 terabyte usable to 38.4 terabyte. We also have inline hardware compression, so that's why you also see a terabyte effective, right? So when you plug in our device, it shows up as for the small 22 terabyte drive. So that way, if your data is compressible, we will expose more logical space for you. We are currently working on our FCM4, and you should hear announcements very soon for that. And again, this currently is only used in IBM storage appliances, but we're looking to expand as well. So let's start with the problem. So IBM has made a commitment to company-wide to protect against cyber attacks and cyber resiliency. So this is a growing problem in the business. As you can see, this is data compiled by our IBM internal teams, but this is just kind of a small subset of what they produced. But you can kind of see for the last 7 years, the average cost is a little under $4 million for an attack, right? Recovering the data, get everything set back up. And you can see last year was the highest at $4.35 million, and that's on average for an attack. So you can see that's a big problem and probably going to continue to grow. So you asked the question, so what does this have to do with computational storage? So an SSD has visibility to the data flowing in the system. It's where the data lives at rest, right? In the FCM case, we can compress and encrypt data with little to no performance penalty, and we can provide other various transforms on that data, again, because it's in hardware with little to no performance penalty. Also, we have intimate knowledge of the access patterns, transfer sizes, logical areas that you're accessing, and also your performance, right? Is there a sudden increase in performance or a drop? And along with that, additional information can also be passed to the drive. So in our case, in our appliance, volumes are spread across multiple drives. The system could tell us which volume this drive is a part of or which volume this logical address is a part of. So because of that, trends and predictions can be made intelligently at the SSD. Okay, so this makes one consider. Block storage, when we've talked to folks about doing ransomware detection in block storage, one of the things that comes up is block storage is missing a lot of context that the other parts of the system have, right? It's the storage. You don't know what application is running. You don't necessarily know what OS, things like that. But it's the perfect place to compute the data that's needed for determining if there's an intrusion, right? So why you may not be able to say that something for sure is happening. Well, you can certainly provide a lot of data for each I/O that might help to determine that. So this makes for an interesting computational storage application. I'm sure everybody's waiting in suspense to hear what that is, right? SSDs can help in early threat detection. So things like ransomware is one of the big ones. Wiperware, where data is destroyed. Turning encryption or compression on in an application, which is also another form of ransomware. And exfiltration, where your data is stolen but not hurt. And so why is this important, right? So computational storage is one of these things that a few years ago, it had so many possibilities. And I think that in some ways can scare people, right? I want to know what my storage is doing, right? And so we feel that it's important to give definition, and this definition is threat detection, providing hints for threat detection. And so not only is it a huge benefit for a money aspect, but it's also from saving the company money, but it's also one of those computational storage features where you don't require applications to know. You don't have to write specific patterns, sequences, transfer sizes. It's all done under the hood by the SSD. And then if it does its job correctly and you get attacked, then you just get a notification saying that something happened, right? So this is as good of a computation as you can get, where there's nothing required by the user other than plugging in the drive. So we've had compression, which is, again, I think one of the best use cases of computational storage. But now, with adopting this intrusion detection hints, so how do we go about doing that? So we wanted to, this is how it ties in with the OCP, right? Is we wanted to develop this on a platform that is more standardized, right? So I'm not sure as much in this conference, but in the other conferences, flash memory systems and some of these others, you'll hear a lot about these technical proposals that are related to computational storage. So the computational programs and the subsystem local memory, or SLM. So we have adopted our infrastructure for the intrusion detection on top of these technical proposals. And so while we are only using this currently in IBM systems, this still allows us to have a platform where we can easily adapt to new computational functions, as well as expand beyond our platforms. So we believe this is the next big thing, right? I mean, there's a lot of other things get thrown out for queries, filtering, and all that stuff is great, and there's a lot of promise. But this is here today, right? We have implemented this in our FCM4 product. So we can provide various I/O analysis to our flash system, and our flash systems run what we call Spectrum Virtualize, or SVC, which many may be familiar with. And then the flash system can provide the user alerts that there's a possible attack, right? And we can even use this with our safeguarded copies to lock down copies if we believe there's an attack, and that way you can easily recover your data. So I'll give you a little bit more of a controller overview. So we are FPGA-based technology. The main processing cores are the APUs. We have real-time cores, and then, of course, the programmable logic, which is the FPGA. So the primary function, of course, is this is an enterprise QLC SSD. So the number one thing with this is we have to make sure we do not disturb that function. And so that's been a big priority for us. So let's go a little bit more in detail. So basically, when the card boots up, it's going to present 3 different namespaces: the base NVMe namespace, the computational namespace, as well as the SLM namespace. And so this is where the host, if configured properly, can take use of those different namespaces. And a little bit more of a picture of how this all ties together. So basically, the way this works is we have statically allocated regions in the SSD. And so the statically allocated regions are basically symmetric for each RPU, and the RPU is a real-time processing unit. It's a Cortex R5F, and there's 2 of them in our device. And so basically what happens is, as data is flowing, for every single I/O, the PL is capturing data, various information about the I/O, and it's putting this all in this data collection area that you can see there in orange. And so as that starts to pile up, the RPU is processing that, and what it does is it provides a summary. And that's what gets put in this green area, which is also in our local memory. And in that summary area is where now the APU has configured with the host to act as a subsystem local memory. So now the host side can come consume the data in that memory, and then it can use it to do the analysis and make some decisions. So basically, just to provide a little bit of a summary here. So we believe that the FCM, in our case FCM, the SSD, is the ideal place to track and analyze data for intrusion detection. So as you can kind of see here, I try to provide a little bit of a graphic. Data is flowing through from the host through the card. We have the information about the data, the size of the data, where it wants to access, the frequency. We can do various data analysis on it, right? So you can kind of imagine what transforms would be good for detecting ransomware. And we also have compression and hardware encryption on board. So this information can all be you can take a small subset of this information, and so for every single I/O, you can put away some metadata in a data collection area. And then the RPUs can then summarize that and provide summaries to the host where it can be analyzed further. So you can kind of think of this, I mean, the way I think of this is we are targeting this for intrusion detection, yes, but it's going to be an unprecedented amount of data that you will have about your SSD, about the workloads, the patterns, the skew, and we'll look at bit for bit. So just that alone, where we can tie into our storage insights, is going to provide users just a tremendous amount of data. And so how does this tie together with our platforms, right? So as I mentioned before, the FCMs currently are used inside of our flash systems platforms. And so along with our safeguarded copy, Defender, and Sentinel, we are creating this whole ecosystem around intrusion detection, right? And so the main goal of this is to reduce or eliminate false positives, right? So when we go through and we talk to various vendors that are buying our appliances, and we talk to them about security, right? A lot of them have programs that they install, and the number one thing is, well, you know, I keep getting these alerts that saying there's been an attack. And then what happens with an attack? The volume gets locked down. So now the admin has to come in, they have to look at the attack, and then they determine, oh, well, that was an attack. Somebody changed something over here. My storage is locked down, and so it becomes a big pain. And so from what we've heard from a lot of these companies is that they end up just turning it off because the amount of false positives is just too much. It creates more work for them. And so one of the good things about the way that we're doing this and the ecosystem that we're providing is that you have multiple drives in the array. So volumes are typically spread across multiple drives. And so we have a layer above that can kind of accumulate that data for all the drives and determine, okay, I see something anomalous is happening here. Do I see that on other drives within the same volume? So now you can make a really good decision with a high confidence level that, yeah, a lot of the SSDs are reporting similar anomalies, right? So this will lead to a great improvement in accuracy for threat detection. So that's kind of the how this ties in to our storage platform. And we believe that, again, today we sell this in our appliances, but we believe we can extend this outside of our appliances, right? We can provide APIs as well as the information needed in order to extend this in other areas. And so that's the end of my presentation. So again, I wanted to tie this into, this is what we believe the future of storage-based recovery. But again, it's built on computational storage, and then tie it into the OCP platform where we're all following a standard process in order to create an infrastructure to allow us to easily adopt things like this and whatever the next great killer app is in this industry. So I want to thank everyone for having me today. I can see you all reaching into your wallets and getting your Cash App out, and so I'll be selling FCMs in the lobby for the next hour. But seriously, if you do have some interest in FCMs, in ransomware intrusion hints, or another killer app, please come find us at the IBM booth. We'd be happy to talk to you, and we'd love to discuss this and other applications in further detail. So I appreciate your time, and thanks for having me here.
Does anyone have questions for Tim? All right, great. Thanks, Tim.
Good.